Well, thank you very much for the invitation. It's a great pleasure to be able to talk here today. So I will talk about joint work with Pierrick, Bousseau, and Andrea Brini. Two papers on this are on the archive, and you can see it written here. So I'm particularly pleased to be talking in Nottingham because, of course, this is a center for polytopes, and so I wanna present some some polytopial manipulations, and hopefully they will be of interest to some people in final search. So that's the slogan for today. Maybe a few comments. So the setting we will be in for all of today is we start with a Looijenga pair, which will be a log Calabi-Yau surface of maximal boundary. This means that Y is a smooth projective surface. In practice, you may really think of Y as being a rational surface. And then we choose a anticanonical decomposition of the anticanonical divisor in L components, and L will always be at least at least two. And we will require each of the DJs to be smooth and neth. If you do the math, there are 19 deformation families of such. But in fact, we can also allow for orbifold singularities at the intersection of the divisors. And if we do that, then we have infinitely many families. While we treat L equals larger than 2 as well, for today I will just focus on L being 2. I have two prototypical examples. The first one is just P2 with boundary, a line and a conic. So you take the, so D1 will be a line and D2 will be a conic. And another example is the degree 6 Del Pezzo surface obtained by blowing up P2 in 3 points. And we take, so the way to think about this is you start with P2 with a line and a conic, and then you blow up 1 point on the line, a smooth point on the line, and you blow up 2 smooth points on the conic. I mean, by smooth, I mean not the intersection, just away smooth points of the boundary. And then you get this DP3 example with this boundary. So it is actually, it turns out it's enough to, if you specify the self-intersections of the divisors, then this actually completely determines what surface you're in. That's why I use this notation. Okay. So yes, so you can just think of these two examples, and in fact, I'm oriented. My talk is examples oriented. The theme is from these Looijenga pairs. We built 5 different enumerative theories, or we consider 5 different enumerative theories which are associated to geometries which are built from Y, D. We show that they are all equivalent. And moreover, I mean, the way we do this is we compute all of them, and so in particular, they're closed form solvable. And then today I describe some of these through examples. Okay, this is a summary of my talk. Well, also, sorry, this is a summary of our work. I'm not going to talk about all of this today because I think I will be talking about plenty. So here we have log Gromov-Witten invariants. We have open Gromov-Witten invariants. What we prove is that they correspond to each other in all genus. So there's this refined log open correspondence. We also have local Gromov-Witten invariants associated to a different geometry. We prove that in genus 0, the log invariants correspond to the local invariants. Then we have some underlying BPS structure, which is the underlying integers of these curve counting theories. There's a relationship due to Clem-Pandey, Yonel Parker between the two. And then there's a relationship here and here due to, okay, the last one is Oguri Rafa, the second one is Marinho, and the first one I forgot. I refer to the paper. And then also we have a correspondence with quivers, which is related to knots as well. And basically what we do is for all of these 5 boxes, we compute everything and we show it's the same. Yes. Okay. But for today, I'm mainly focusing on the diagonal, on the anti-diagonal, because there's just too much to talk about. Okay, so let me start by saying something about what the geometric mechanism is to go from log to open. So this is the bit where I hopefully appeal to your toric soul. And here I'm looking at the example of dp302. So we start with P2 with a line and conic, and we blow up a smooth point on the line and 2 smooth points on the conic. Now, in order to do this construction, first we need to consider a deformation where D1 becomes toric. So if we just do these generic blowups, D1 will not be toric, but if we blow up 2 points infinitely close, then we really get a toric surface whose fan is given down here. So this was the fan of P2, and then we blew up first E1, and then if we did this generically, we would blow up a point here and a point here and a point here. However, we do this non-generically. We blow up a point at the intersection of these 2 divisors. This creates this -2 curve here, but it's all good. And because we did this now, H minus E3 is a toric divisor. Okay. And now we can look at its associated polytope. Maybe if you're a purist, you will say that the my polytope is drawn upside down, but I don't care. And so yeah, so it's just the dual polytope. And so that the next step, what we're going to do is we remove D1 and we replace it by framing. So here you can see the out. Here was the previous polytope I'm showing you right now with my mouse. I hope you can see it. And so this is the edge we removed. And so if you want, this corresponds, you remove this divisor in the surface. And then the polyhedron you get by extending these edges to infinity is the polyhedron associated to that toric surface. We don't care about that. We just replace this dashed line with a dashed arrow, which we call a framing, because it's fancier. And then what we do for the remaining vertices is we just balance them. So we add array at each, such that each vertex is balanced, which means that if you look at the primitive vectors going out from the vertex in the directions of the edges, they sum up to 0. Yeah, okay. So that's the process. That's the geometric, the polytopial manipulation I hinted at. And in fact, what we just did is we built a toric Calabi-Yau graph. So the underlying geometry is you take you start with this dp3 and then you remove d1, you consider the canonical bundle on it, and you take the total space. So this is a toric Calabi-Yau threefold, and what we've drawn, it admits a SYZ type torus vibration, and what I've drawn here is the discriminant locus of this vibration. And the framing determines one of these Arganagic-Schwacher Lagrangian A-branes. And so if you come from a different I don't know enumerative school, which is the school of like open Gromov-Witten theory of toric Calabi-Yau threefolds, maybe some keywords for this are topological vertex, topological recursion, etc. Then that is something you'll be intimately familiar with. And so what this construction did is we started with something which was built from a Looijenga pair. In fact, the Looijenga pair we started with is not toric at all. because D2 is not a toric divisor. Or in other words, if you take the complement of D1 union D2, then you don't get C star squared. So it's not toric. We did some manipulations that brought us to a toric Calabi-Yau free. And this process is perfectly reversible. Yeah, so that's a geometric connection between Looijenga pair and toric Calabi-Yau free. What we did is in our surface we designated D1 to be open, and we designated D2 to be local. So we started from the fan and we removed D1. We replaced D1 by this open condition, but we kind of remember it for the framing. And then we twisted by the remaining toric rays, and I'll say a couple of words about this in a second. And this gave us toric Calabi-Yau free, and this construction. So there are some conditions for this construction to work, which is related to we want the remaining toric rays, the sum of them, we want it to be Neff. And in the initial deformation that we considered, we introduced these extra -2 curves that generically are not there. And what this can do is they can lead to non-Neffness of the sum of the remaining toric rays. And that's why it doesn't work for all 19 deformation families, but only for 15 of them, because we really want this Neffness condition for the twisting part, for the local part. I'll explain this a little bit better now. Okay. So if we just ignore the framing, what I did is the following thing. So we started with this a fan, and this one was D1. We removed D1, where we get this fan here, which now gives us a non-compact surface. And now we want to twist by the remaining toric divisors. So what this means is we take each of these rays and we lift it to height 1. So this one was -1,0. We lift it to height 1, so it will be generated by -1,01. This one was -1, -1. We lift it to height 1, so it'll be generated by -1, -1, etc. And then we get this 3-dimensional, and very importantly, we add one extra ray here corresponding to the origin, which is just directed by 0, 0, 1. So when we lift up these rays in the vertical direction and add this extra 1 at the origin, we get a fan, which is the cone over these unions of triangles. And that's exactly the fan of the toric Calabi-Yau free that we constructed. So in this picture, and the way you can see this is if you start with this union of triangles, and now you draw the dual graph, you will exactly get back this dual graph, except for the framing. And so the framing we need to remember. By the way, maybe you were wondering why is the framing here and not here. So you make a choice. So you make a convention that the framing is either pointing in the clockwise direction, corresponding to the vertex it's associated to, or in the anti-clockwise direction, and then all choices are canonical. So are there, maybe if there are any questions for this picture or this picture, maybe now is a good time. Yes? Was there a question? How do I define gradient? Oh yeah, yes. So excellent question. So in my case, in the case, what I'm doing here, the framing is just a vector that is associated to one of these rays, and it has to I have to be able to write f as the sum of this PV1E2 minus a multiple of PV1E3. And then this multiple is going to be the framing. In this case, this F is equal to this minus this one. So the framing is -1. Now, well, you maybe, so that being said, this can be generalized a little bit in the orbifold setting, where we can have sort of fractional framing. But maybe what you're wondering about is what if you're interested in toric Calabi-Yau threefolds, and then you would you might think of these framings in a slightly different way. But I don't want to go into this. For us, it's really just we had this edge here, and we kind of cut off the edge, right? We cut it off here, and then we just remember the direction this edge was in. And because we're doing toric geometry, we can write this F as the sum of this minus a multiple of this one, and we declare that multiple to be the framing. And that's all the information that is needed to compute the open invariants later. And so if you talk to someone who studies open toric Calabi-Yau threes, they will tell you something else about what the framing is. But for us, it's really just a way of remembering how we compactify in that infinite direction. So in summary, we want to remember the compactification, and the framing does that from our point of view. I hope that kind of answers the question.
Yes, thank you.
Yeah, well, thank you for the question. Are there any more points, comments? Maybe you're displeased with my choices of colors, or okay. And then here that was just a fan drawn in case you like this sort of thing. Okay, so then I will move on. So in this whole story, remember we chose one of the divisors we declare was an open, and we declare one to be local. So we removed one and we twisted by the other. But we could also have twisted by both. So we could have declared both D1 and D2 to be local, and then we would have done the same twist here for D2, which is the sum of these rays. But then we would have done an additional twist for D1, so we wouldn't have forgotten this D1, but we would have twisted it in an extra fourth dimension. So this ray, which here is 0, 1, we would have, is directed by 0, 1, we would have directed it by 0, 1, 0, 1. Then we would also have added a ray in the direction 0, 0, 0, 1. And then given all these rays, we just look at the fan built from this, and that gives us a toric Calabi-Yau 4. And if you didn't follow what I just said, all I did is I described the fan for the total space of O minus D1 plus O minus D2 on, in this case, DP3. And so that's another way you can, in this way, you can build a Calabi-Yau fourfold associated to the Looijenga pair. And in general, it will not be toric, but we don't care. You can always deform it to a toric one at the price of creating some -2 curves or worse. It could, or -3 curves can occur. And another thing we could have done is we could have declared both D1 and D2 to be open. So we could have removed both divisors. And in fact, when we have 3 components, we do remove 2 divisors, and when we have 4 components, we remove 3 divisors. However, in the case with just 2 components, the problem here is if we remove D1 and D2, that's all well, but we don't have known techniques to compute the associated open Gromov-Witten invariants. So in fact, we only have tools to compute open Gromov-Witten invariants for toric Calabi-Yau threefolds, and the tools are typically topological vertex, topological recursion, etc. And so, because we want to be able to prove some things, we always need, if we want to compute something about open invariance, we always need this toric Calabi-Yau free condition. Yeah. Okay, so that's just a comment. Feel free to interrupt me anytime, of course. So summary so far. So we started with 19 Looijenga pairs, and then for all of them, we can build the local Calabi-Yau 4 folds or 5 folds, or L, in general L plus 2 folds. For 15 of them, we can build these open toric Calabi-Yau free geometries. And out of those 15, the 10 with L equals 2, there's also some associated quivers. Yeah, and I'm not saying much about quivers today. And so to each of these geometries, we and I should say I say 19 here, but again, if you allow for orbifold singularities, then you have infinitely many of all of them. And in fact, you know, in Nottingham, probably you really do want to have orbifold singularities, and so this is all good. Okay. And then so someone is asking for, well, something. I'm just going to ignore it. Oh, okay, yeah, so I'm just going to ignore that. And then, okay, so now I'll say something about the enumerative theories. As I told you, we build some geometries, and which also we build some quivers, and to each of them we have some enumerative theory, and we show they're all the same in exactly the typical way that people do this in, but when they do this sort of things is we compute everything and we find agreement. And so first I will just focus on P214, which is P2 with D1 a line and D2 a conic. So this is so P2 with log Calabi-Yau boundary given by a line and a conic. And so the first invariants I'm going to introduce are the log Gromov-Witten invariants of maximal tangency. So for this, if we were looking at degree D rational curves in P2, the space of these is of dimension 3D minus 1. And then in order to actually formulate enumerative questions, we need to impose some conditions. And some of the conditions we can impose is we can ask the curves to pass through a point. That's a codimension 1 condition. We can ask a curve to be maximally tangent to a line or a conic. So if you have a degree D curve in P2, it will meet a line in D points. And being maximally tangent means we want all of these D points to coincide. So we're squeezing them together. And every time we move 2 points together, that's a codimension 1 condition. And we do this D minus 1 times. That's why being maximally tangent to a line is a codimension D minus 1 condition. Being maximally tangent to a conic is a codimension 2D minus 1 condition. And so if you do the math, if you sum 1D minus 1 and 2D minus 1, you get 3D minus 1. So in other words, the following enumerative problem is well defined. We're counting degree D rational curves in P2 that pass through 1 point and that are maximally tangent to a line and a conic. So line and conic being our divisors. So this is an image. So here we have this point our curves have to pass through. It meets the line in 1 point of tangency 6. It meets a conic in 1 point of tangency 12. It's of degree 6. The number is 924. And I know this not because I found them, all of them, but because we compute this. We compute that this number RD is 2D choose D. And I will say how this computation works a little bit later. So in summary, that's the enumerative problem for our surfaces, and that's the image you may as well keep in mind. So for now, I restricted to genus 0, but later I will say something about higher genus. And in fact, for the surfaces, you can do everything in higher genus. Okay. And now we apply our construction from before, and if you look at this picture, if I just drew this triangle, that's the polytope of P2. where this edge here corresponds to a line, and then the sum of these two corresponds to the conic. Then I remove this this edge, I replace it by a vector. Now in this case, the framing I told you orally is you take this minus a multiple of this one, and so you see that like this ray is this minus this one. That's why the framing is 1. And then I balance by adding this extra ray here. And here's the picture again, but kind of so the geometry is C3, and this is the discriminant locus for the toric Calabi-Yau threefold, which is C3. And then this framing is along one of the axes, and it determines one of these Lagrangian A-branes. So here's a little picture of this. So we have the coordinate axis in C3. We have this Lagrangian, which should be 3-dimensional, and then we have a disk. In fact, the disk is localized on that coordinate axis. It meets the Lagrangian in an S1. So there's an associated count of this, which is goes back to Katz and Liu. So we're counting disks in C3 that have boundary landing on L. They need to have winding number D, so they wind around D times at the boundary, and the framing is 1. And this invariance is defined by localization. And if you do the calculation, you find that O of D is this expression, a sine divided by 2D squared times the 2D choose D. And so if you compare this with what we had before, and a priori there's no reason to expect there to be a relationship, but you find that OD and RD differ by a factor of a sine divided by 2D squared. And it's not an accident. So basically one of the first results we show is that exactly that relationship holds true for all cases. And then we generalize this to higher genus. Let me say a little bit something about the Calabi-Yau 4 geometry. So now we twist by a line and we twist by a conic. So we're looking at the total space of O-1 plus O-2. And we have some. Yes?
Arkady.
So could you maybe say something about, because you said that you can argue from geometry somehow, or rather you didn't say that explicitly, but you had this formula. Couldn't you explain why you should, like what the idea is behind why these are related?
That's absolutely excellent question. So let me go a little bit forward here. You were 10 slides ahead, but I might as well say it like this. So we think about, we have here is a weird drawing of one of these rational curves that meets this line in one point of maximal tangency. So in particular, there's this little disk here, and what we will do is we take this line and we take a tubular neighborhood of it and we remove it. And if we do this, what we've done is we cut off this little disk here by some conjectures due to Oru. There is supposed to be this cutting is supposed to be along some Lagrangian, and which separates this like now two disks. So we have a disk on the left-hand side and a disk on the right-hand side, and they both meet the Lagrangian in winding number D. So basically this process of going from lock to open should just be that I take a tubular neighborhood of my divisor, I cut it, and then what remains is now a disk that has a certain winding number with a Lagrangian, which was, you know, close to the divisor we cut off. So this can all be made perfectly precise. However, this conjecture is not proven, but you can describe what you expect. So this is what we expect. Now that being said, there's this extra twisting which I'm ignoring this explanation. But basically, we have these conjectures coming from symplectic geometry, We cannot, like this geometric transition I just described to you, we cannot go through it because we just don't have the required techniques. So maybe, I mean, at least I certainly do not. However, what we can do is we can compute both sides and we find agreement. Now, maybe you're wondering, what about this factor? Well, when we did this cutting, actually there were a certain number of choices there were a finite number of choices where we could have met the line. And so when we do this cutting, we're choosing one of these point of contacts, yeah. And so by doing this, we're ignoring other curves, and that's why we have to account for this factor here, yeah. And then the sign is just because there's always a sign, and no one knows why. Yeah, I hope that's a somewhat satisfactory answer.
I think just maybe make sure the point is you don't. So this is kind of a geometric motivation, but there isn't a precise geometric. Is that?
So there is. Yes. So that's an excellent point. So there is a heuristics, but this heuristics, to the best of my knowledge, cannot currently be made precise. So maybe someone knows how to do this, because I mean, there's all sorts of problems. When I described this to you, maybe it seemed reasonable. However, you shouldn't forget that we're looking at moduli spaces. There's multiple covers, and there's a bunch of mess, and that's why it's only heuristics at this point. But maybe someone in symplectic geometry knows how to make this precise. The problem is it's extremely hard to deal with these disks. Basically, if you really want to look at moduli spaces of disks or Riemann surfaces with boundary, and this is not algebraic geometric, so you cannot use tools from algebraic geometry, and it's really difficult to deal with this. I mean, there's been recent work by Tukachevsky and Tesla and Salomon and probably others. But still, it's really hard to be able to work with them, and it's very hard to compute them. The only place we know how to compute is in this Katz-Liu setting of toric Calabi-Yau trees. Yes, so there's a heuristics. We completely avoid the heuristics by just computing everything. So the advantage is we have computations. Maybe the disadvantage is that it would be nice to actually understand the geometry better. Yeah.
Thank you.
Yeah, but really you can see this. You can see this like framing. We're cutting off. We're removing an edge, and we kind of want to. This Lagrangian remembers how we compactified, or how like the Lagrangian remembers how we need to compactify to go back to the Looijenga pair. Yeah. But yeah, thank you for your question. It's an excellent point. Okay, so maybe now let me just say, let me just give you an overview of the local Calabi-Yau force. So maybe some of you will care most about this because there's extremely exciting work going on about enumerative geometry of Calabi-Yau force. So let me just say a few words about this. So we do this twisting. We count rational curves in this Calabi-Yau 4 geometry that pass through one point. There was a calculation by Clem Pandey, which we reproduce in 2007, which computes that this these numbers ND is equal to this. So you can, in particular, you can see that it's exactly the same as we had here, right? And it's also related to this RD by this factor. One thing they did at the time in 2007 is I should say, so this isn't. So throughout enumerative geometry, you have this like recurrent theme where you go through all these pains of defining some numbers, and then you end up with rational numbers, which is kind of inconvenient if you're supposed to be counting rational curves. And so there's always these constructions where you're trying to you're trying to find the underlying integer invariance, and usually this works by conjecturing that. Or stipulating that the only bad components are of the moduli space are multiple covers, and once you account for this, you're supposed to be obtaining the actual number of curves. That heuristics is not precise, but still miraculously we always get integers in all known cases. So we, by this formula, we can define new invariants KPD through this formula, and they conjectured that those were integers. What they didn't do is, and this is completely reversible. Using Möbius transform, you can express the KPD in terms of the ND. So what they didn't do is they didn't plug it in the Encyclopedia of Sequences in the OAIS database. And if they did, they would quickly have found that there's lots of entries for this. In particular, it has to do with parking spaces, but also other ones. But instead, let's just take this little formula and invert it first. So this is Möbius inversion. It's exactly the same formula, except we have this Möbius factor, which is plus or minus 1 or 0, depending on the primary decomposition of K. And then we can simplify this. We move the d square out, the k square simplify, and then we replace d over k by k. We can get rid of the 2 by incorporating it into this binomial coefficient, and then we find miraculously that this is a quiver dt invariant for the quiver with 1 vertex and 2 loops. So there's a whole theory of this. Maybe I don't want to go into it. We're looking at representations of quivers, and we can associate the dt invariants. In this particular case, Reinick in 2012 computed this and got exactly this formula. So here we see for the first time how one of these invariants relates to quiver dt invariants, and we generalize this to a lot of the cases. Okay, so in summary, those are the 4 different geometries. Associated to this, we have low Gromov-Witten invariants of maximal tangency. Associated to this, we have open Gromov-Witten invariants. Here we have these local Gromov-Witten invariants. Here we have quivers, and then there's this BPS structure that underlies all of them, and we find that even though those are different geometries, different dimensions, we get equivalent invariants. And this is interesting because now you can take a probably very hard structure in one case and move it to the other geometry, and maybe that hard structure suddenly becomes very simple. Okay, any questions so far?
Is the quiver, does it have framing on the vertex, or is it just
for the quiver, so I think there's no framing. Okay, so there's no superpotential. No. So is framing the thing where you add another vertex and then you add. Yes. Oh yeah, sorry. Then yeah. So apologies. Yeah. You introduce the framing in order to define the invariance. Yeah. So sorry for that. Yeah. So you introduce this framing where you add an extra vertex, you add extra arrays, and then you define the invariant thanks to I think. Once you add the framing, you have like 2 stability chambers, and then the wall crossing, the coefficients that determine the wall crossing give you the dt invariance, so something like this. Yeah. Yeah.
Thank you.
Yeah. Well, thank you for the question. Okay. Yeah. So maybe since obviously. There's some interest here. So one of the highlights of this work is that we get a refinement of these invariants. This is something I will talk about at the end. When you're looking at the BPS invariance of this open geometry, which in this case also is the BPS invariance of this geometry, and then you refine them by higher genus, that gives you a refinement of these numbers here. And that's, I think, very interesting because these numbers are very, very heavily studied in recent years. In the work of Joyce Borisov, Thomas O, Arkady did a lot of work on this as well. And then we get this kind of refinement for free that pops out of nowhere, and we don't know what it means. But maybe maybe Arkady or maybe someone else among that community will eventually be able to tell us what that refinement means. And yeah, anyways, okay, so I have a few, I'm also watching time, but I have a few slides about just the sort of things we do. So first, this is local business. It goes back a long 20 years to work of Takashi, Gatman. We did some work on this in the case of one divisors with Graeber and Woodard. With Bousseau and Brini, we extended it. We looked at several divisors in the toric case and in this work in the in some non-toric cases as well. Nabijou Ranganathan proved this correspondence at the cycle level in some cases, but also found counterexamples in others. So all cases, I mean, I guess these cases that I mentioned are numerically true, and they found some counterexample cycle level. Tseng Yu looked at related the whole thing to orbifold. I mean, there's a whole thing going on here. Very exciting work, lots of people. And just maybe in one slide, what we do here is we twist by instead of having this conic with this maximal tangency condition, we twist by O-2, which gives, in this case, gives us a I mean, three-dimensional geometry, and then log Calabi-Yau threefold, and then somehow the point is that the invariants stay the same after you multiply by this factor. And so, as I said, you can do this with several divisors. There are some counterexamples. There's cases where it works. Very interesting stuff. But then log open is exactly this cutting that I mentioned earlier, where we take a tubular neighborhood of our divisor, we cut, and then on one side we have this little disk, which is a little disk in the normal bundle. And then on the other hand, on the other side, we have this bigger disk, which has a boundary on this Lagrangian, which is a Lagrangian which is near the divisor. There were a choice of contact points, which gives this factor you need to multiply with. And then in all cases, we checked the invariants on the left-hand side correspond to the invariants on the right-hand side. And now I should say that really what we do is we combine both, because we twist by the conic and we remove the line. Yeah. And we do this because otherwise we don't have we cannot compute the open invariants. We can only compute them when we're in the toric Calabi-Yau free case. So in summary, curves in the Looijenga surface correspond to disks in the open Calabi-Yau free. This story works in higher genus. I'll say something about this. And then we also have this twisting, which I don't talk too much about. So here's the higher genus version. I hope some of you like quantization. And so we have a positivity assumption, which is not so important. And then to each of the Looijenga pairs, we have this open geometry, which I described to you. And then we have this equality of up to a factor, this equality of generating functions of higher genus open and low Gromov-Witten invariants. So here these brackets are the Q integers. The generating functions are expressed, are generating functions in Q, and that's the relationship. Maybe, yeah. That's what it is. If there are no questions, let me move on and let's try to stick to the time. So yes. So you are, a lot of people in Nottingham are a community that is extremely good at, solving problems in algebraic geometry by looking at some limit where things become toric. So I wanted to also say a little bit about how we do this in our case. And in fact, the way we compute the log invariance is as a kind of using the Gross and Siebert program, which for the purpose of today, you can think of as a souped up version of toric geometry, like an enhanced version of toric geometry. And so for us, a scattering diagram, so we will have a complete fan and we will add focus singularities on the ray or on some of the rays. Let me explain this by example. So we start with the fan of F2, the Hirzebruch surface F2, and then and this is if you forget this orange thing, this is the polytope of the Hirzebruch surface F2, and then we declare that, well, if we wanted to modify this in the toric way. We could blow up these toric points, this one, this one, this one, this one. We can weighted blow-ups, whatever. But what we want to do is we want to blow up smooth points on the boundary. This is a fiber class. And we want to blow up a smooth point on the fiber, which here we indicate by this little orange wiggle, and here by a focus singularity at that point. And we say that this is the scattering diagram of P2. If starting from this, we can perform a sequence of toric blow-ups and blow-downs. I mean, we can blow up and these points and blow down straight transform, I mean, which corresponds to, adding rays and removing rays. And if by sequence of toric blow-ups and blow-downs, by sequence of logarithmic modifications, we get back to P214, then this will be a scattering diagram for P214. Why should that make sense? Well, Gross-Siebert program is dictated by Gromov-Witten theory. Gromov-Witten theory is invariant by logarithmic modification. This sequence of toric blow-ups and blow-downs are logarithmic modifications. Therefore, all the enumerative information will be the same. Just we need to remember that we allow ourselves to blow up some smooth points on the boundary. And this changes the interior, obviously, because that thing no longer is toric. And now usually in toric geometry, the interior is C star squared or C star to the n. And so there's not much happening in there. But because we blew up, we suddenly have more disks in the interior. So if you think about if I'm approach, let's say we look at the SYZ vibration of just a Hirtable surface, which is generically has T2 fibers. It's just the moment map. And then if we move to the boundary, what happens in these T2 fibers is that one of the S1s shrinks to 0. And when we hit the boundary, we just have S1 and no longer a 2 torus, a 1 torus, if you want. And in this process, if we follow a vanishing cycle, we get a little disk. So, and that little disk in the Hirtable surface has intersection with the boundary. So that means we always need to take it into account when we do enumerative geometry, because we want to take into account all the intersections with the boundary. But now, because we blow up exactly that point where this disk meets the boundary, we push this disk inside, and now suddenly we have a freewheeling disk inside that can do all sorts of things. Yeah. So we created a Maslov index 0 disk that has no intersections with the boundary, and now that can do all sorts of wild stuff. Yeah. And I'm drawing it as a wiggly line because if you take the sort of Gromov-Hausdorff limit, it becomes a wiggly line in the polytope. Now, however, if we look at the dual picture, which is this scattering diagram, it's no longer a wiggly line, but it became a straight line. It's a wall. And it carries a wall crossing function, in this case 1 plus t to the x minus 1. And this wall crossing function is encoding a lot of the enumerative geometry of that Maslov index 0 disk. Yeah. And so this is about the disks that exist already and that are ready to mingle with broken lines. So now let's say we want to do a rational curve. We want to consider a rational curve, and we want it to have maximal tangency with D1, which in this case is this divisor, and D2, which is this divisor. We don't care about the other two because they don't really belong to P2. They were just created by toric blowups and blowdowns. Yeah. So we want a disk that comes out from this divisor with tangency, in this case 2D, and from this one with tangency D. And again, if you look at the Gromov-Hausdorff limits, those are some wiggly lines, and obviously we want to kind of join these wiggly lines. I also put a point here because we also have a point condition, if you remember, otherwise we don't get a finite count. Now again, on the scattering diagram, these wiggly disks become straight lines, or these on line segments. They're always straight. I mean, they're line segments and can bend. And And that's really convenient to work with. So we have one that comes from the direction of D1. By the way, if we chose another direction, this would mean that it comes from like the intersection of some of these toric points, or comes from divisor, which are the weighted blow-ups of these points. But let's ignore this. Okay, so I start with a broken line, in this case, that comes from this D1 direction. It carries a weight, which is exactly the tangency. And in this case, it's D. In this case, it's 2D. So D1 is this direction, D2 is this direction. Now, when these broken lines, maybe that's the next slide. When these broken lines meet the muzzle of index disk, they can do two things. They can either just pass right through, or they can pick up a contribution from the muzzle of index 0 disks and continue with this extra contribution. And now, at the end of the day, we have some tropical curves, and they all need to satisfy the balancing condition in order for them to correspond to holomorphic curves. So when it crosses the wall, it can pick up different contributions of the muzzle of index disks, and we need it to pick up the contribution that is such that the curve will be balanced at this point P. There's only one choice. Another way of saying this is that, well, this focus singularity, or this blow up here, when we go all the way back to P2 through the sequence of logarithmic modifications, this corresponded to a line. And our rational curves meets a line in D points. That's why this T needs to be picked up with a power D. And okay, so just in a summary, there's only one way to cross this wall, and by doing so, this broken line picks up a coefficient, which is this binomial coefficient 2D choose D. And this is exactly our Gromov-Witten invariant. One way to think about this is a enhanced version of toric geometry, where we add in these focus singularities. And as for toric varieties, you have a correspondence between rational curves and tropical curves. Now we have a correspondence between rational curves and tropical curves, where these tropical curves are a little bit different because we have these focus singularities, but they again carry multiplicities, and the multiplicities are exactly the invariants we're interested in. So we produce a coefficient. This is the result of a multiplication of two broken lines. So this broken line with this broken line, they had asymptotic monomials, which were dictated by the intersection multiplicities with the divisors and the directions of the divisors. And to be a little bit more precise, we really looking at the identity component of the result of multiplying two broken lines. And if you sum over all the possibilities of doing this, then this gives you, then each asymptotic direction corresponds to a theta function, and then we multiply two theta functions. And so just the theorem due to Mandel, Kiel, Gross, Siebert, which is a proof of a conjecture stated by Gross, and Kiel in 2011, is you start with low Calabi-Yau surface with scattering diagram and curve class, and then you let R little rd to be the sum. You take all the possible broken lines with the correct asymptotic monomials, you multiply them, and then you sum the coefficients, and that RD is our log Gromov-Witten invariant. And that's why in this case we got that the invariant was a binomial coefficient. This is the image that computes this, and this is your introduction to the Gross-Siebert program. And for the purpose of today, it's just a really a great way of counting curves. So I have some more examples where now we have two walls that interact. The interaction is simple because the determinant of the directing vectors is just one. Nonetheless, you pick two binomial coefficient, crossing this wall picks up this one, crossing the next wall picks up the next one, and that's our invariant. In this case, it's F1, 1, 3. You can also have infinite scattering, which is, in this case, this is F104. These two broken lines, the determinant is 2 or plus minus 2. This creates infinite scattering. So when this broken line comes, it has infinitely many possibilities of bending, but it will only bend a finite number of times. So the invariant of this will be a sum over all the possible ways of products of binomial coefficients, all the possible ways of the bendings, of products of the associated binomial coefficients. And then we have some reason to believe that this invariant is for here is the same as this invariant for here. So meaning that this product of two binomial coefficients is this sum of products of binomial coefficients. So we stated this as a conjecture. We sent it to a combinatorialist, Kattenthaler, in Vienna. And a few hours later, he gave us a proof of this, which is quite remarkable. So you can view this as a way of generating new binomial identities. Here we have DP311. We have 4 focus singularities. There's a little bit more complicated scattering, but there's just still only a finite number. And then we can do the same thing with 2 pointed invariants. So now we have 3 divisors. And so we have to multiply 3 broken lines, but it's again the same principle. Here we have a psi class, which means we have one 3-valent vertex. We can get rid of the psi class by replacing it by 2 point conditions, which means that we need to give this vertex its tropical multiplicity, and we multiply everything together, and that gives us our invariant. Now, I do want to say a little bit about a refinement, because I know it will be interesting to some people in the audience, including Arkady. So I'm just doing by example. Let's look at, and so this will be the last couple of slides. So let's go back to P2 with boundary line and conic. Now here I remember Clem-Pande defined these BPS invariants. And here I'm just giving you the Möbius transform of their definition. So the KP invariants can be defined from these, the local Gromov-Witten invariants associated to the Calabi-Yau fourfold via this formula. And this is exactly also the formula. We know that these invariants are open Gromov-Witten invariants of Calabi-Yau 3. There's a well understood multiple cover structure, and so this formula exactly gives you the BPS numbers for the open Gromov-Witten invariants of C3 relative to Lagrangian. And now we just take this formula and refine everything by higher genus. So we just replace this by higher genus. So first maybe just a quick definition. The local Gromov-Witten invariants of higher genus. If it was genus 0, then you wouldn't have these 2 terms. You would just integrate over the fundamental class of the moduli space. You would take a point class, the pullback of a point class, because you want the curves to pass through a point. In higher genus, you add this lambda class. This is the top term class of the Hodge bundle, which is a vector bundle of rank G on the moduli space. Given by the dualizing sheaf. And then phenomenal work of Bousseau Pierrick Bousseau in 2018. He quantizes the scattering diagram exactly for surfaces, the ones we saw, and shows that the quantized scattering diagram computes the generating function of these things. More precisely, I'm writing the generating function here in h bar. So just the usual thing, h bar to the 2g with the corresponding coefficient summing over all the g's. And then we have to make a change of variable, which is setting q to be e to the I h bar. In other words, we replace this h bar by minus, or if you want, by the power series expansion of minus I log q. So this corresponding to this change of variable. And then we find that the invariant, or this generating function expressed in the new, in Q, is this quantized binomial coefficient, which is just, the coefficient of x to the d in this expansion. You could also write it as, the Q number of 2d times the Q number of 2d minus 1 I mean, if you want the q factorial of 2dd divided by the q factorial of d times q factorial of d. Anyways, and then this is again in a different color, but still the same result, the relationship between the two sides. But now, why is this interesting? Well, remember, this is the multiple cover formula for open Gromov-Witten invariants, and now you start with this formula, and you just extend it to a higher genus. And this was done by Oguri Rafa. So this is about disks. They tell us how to refine this formula, how to extend it to higher genus. And so this produces a lower polynomial refinement, omega dq, of these BPS numbers. And it has the properties that if you set in this polynomial, if you set q to be 1, you get back the BPS numbers, which are the KP numbers. So which are exactly these invariants of local Calabi-Yau fourfolds, which are generating so much interest. So again, we have this, we produce this lower polynomial that specializes to these very interesting invariants. Moreover, they have this integrality properties. I mean, they're integer, well, up to this q factor, they're integer. Oh, sorry, they are integer lower polynomials where you can replace q by q minus 1 and it won't change a thing. And you can, here are the first few terms. And somehow these numbers that you see here, minus 1, 1, minus 1, 1, 2, 6, 5, 1, they're supposed to be actually the real underlying numbers for this Calabi-Yau fourfold. And now the question to the audience, what does this mean? I mean, we know what it means for the toric Calabi-Yau threefolds, but what does it mean for the Calabi-Yau fourfolds? And so in summary, well, we show lots of things. So we start with one of these Looijenga pairs. We look at this Calabi-Yau, it's associated Calabi-Yau threefold. We prove higher genus log open correspondence. We have these higher genus open BPS invariants, which are lower polynomials with integer coefficients invariant under replacing q by q minus 1. And crucially, they provide this refinement for these KP numbers. And we're waiting for someone to tell us what this means for Calabi-Yau fours. And my final slide. So these are all the correspondences. I focused mainly on the diagonal, on the anti-diagonal, but there's much more to be said about the whole thing. And yeah, thank you very much for your attention and patience.